All right, thank you everyone for joining us this evening. Welcome to North Coast Land Conservancy's On the Land series. I am Lynette Villagomez, the NCLC Outreach Manager, and I'm joining you from Seaside this evening. For those of you who are new to NCLC, I can give you a little intro. NCLC has been a conservation organization since about '86. And the work that we do connects the landscape of the Oregon coast from the Columbia River to about northern Lincoln County. And we acquire or otherwise manage lands for their habitat value. NCLC has a portfolio of more than 50 fee title properties, so land that we own outright, and in addition to more than a dozen conservation easements. And we are a nationally accredited private nonprofit land trust, and we work to ensure that this extraordinary region is a place where healthy communities of people, plants, and wildlife can all thrive. Currently, some of you may have heard of the project that NCLC has undertaken, which is to preserve the Rainforest Reserve. It's a 3,500 acre property that serves as a backdrop for many of our North Coast communities in Clatsop County and Tillamook County. And to find out more about our work, you can visit nclctrust.org. And if you can see my background, this is the Rainforest Reserve here. We are so pleased that you could join us tonight. Normally, if you're familiar with the On the Land program, we would be meeting outside on the land and in person. But as we know, things aren't and haven't been normal for quite a while. So this is what we're doing. In lieu of canceling our On the Land events, we thought we'd bring the land to you. Thank you all for joining. Some housekeeping items. Please be sure to keep yourselves muted now and throughout the presentation. When Tom is done presenting, we will allow some time for questions. And if you do have a question, you can ask in the chat. I'll try and monitor that. And then, but save that to the end so it doesn't get lost. And then you could also raise your hand and I'll call you. And then you can unmute yourself when I call your name to ask your question if you'd rather do it that way. And in order to raise your hand at the bottom of your Zoom screen, there's a little button that says reactions. If you click on that, there's an icon or a bar at the bottom that says raise hand. So tonight, many of you are probably familiar with Tom Horning, but I'll give him a little intro. Tom is a local geologist. He grew up in Seaside and he earned his master's degree in geology at Oregon State University. He returned to Seaside in the 90s and opened Horning Geosciences, a geological consulting service. And Tom joined the board of North Coast Land Conservancy in 1996 and has been actively involved with NCLC ever since then. So Tom, if you're ready to screen share and begin your presentation, I will leave it to you to begin. Thank you all for being here.
Thank you, Lynette. It looks like I've got my screen up, so I'm assuming everybody is sharing and seeing it okay. Is that consistent, Lynette?
I can see your screen, yeah. I can see your PowerPoint.
Okay. Okay, well, thank you. This presentation was inspired in part by the Rainforest Reserve project that we've been going on for the last 5 years. And so there will be a few introductory photographs to show why we're doing it and hopefully without being too repetitious. Now, I'll hasten through this because I've, as usual, got a few too many slides for the amount of time that we have. I'm budgeting about 60 minutes and I might need an extra 10 just in case. Let's see here now. First, I want to give credit to Al Neem, professor of geology at Oregon State, who's work with graduate students overseeing their master's theses mapping projects, map the entire county. And I want to especially acknowledge Carolyn Peterson, who's on our witness list. She's watching the show. She did her master's thesis near Sugarloaf Mountain, as I recall. So Carolyn, I told you I'd do this someday. Al's a crazy man. He will take apart a rock all the way down to its isotopes if he's got an opportunity. They call neeming a rock a term for deep analysis of a rock, especially down in Southern California, where Al's done a lot of independent research. So the area, this is Clatsop County, shaded relief map. If you look down in the lower right-hand corner, lower left-hand corner, let's see, I've already got screwed around by this thing. We have 3 properties that the blue one are the Land Conservancy Project. The red one is the Community Forest Project for the community of Arch Cape. And we're going to be focusing most of our talk from Tillamook Head down to Cape Falcon and Yukon Mountain, but we will go all the way over to Nikolai Mountain and a few other places farther in between. The area is known for its rugged relief. You can go up over 3,000 feet in less than a mile from the ocean. It's the only place on the Pacific coast where such rugged terrain fronts the ocean so steeply. And as you know, habitat is proportional to temperature and rainfall, and these mountains get quite a lot of rain, and they experience quite a change in temperature up to glacial or Arctic conditions at the top. So it's creating quite some unusual habitat. We've had many different groups for fundraising and for background education out on the land. This is a photo up looking north towards the north property boundary, which runs near the clear cut. As you can see, this is the second clear cut for these mountains. Most of this area was clear cut back in the 1960s and a little sooner. It's known as the Van Vliet forest lands, and they took just about everything. Let's see. So I threw in some flowers. I'm not a botanist, but I looked up their names, and as near as I can recall, it's quite a salad of beautiful wildflowers up in the grass balds on the tops of the mountains and wherever there's road cuts. Of particular importance is Filipendula occidentalis, a couple of other places, Saddle Mountain and over on the north side of the Columbia River, just near Chinook. There are penstemons, there's Chambers paintbrush, which has just been identified as a distinct species, and ever-present lobatium. This is the Columbia lily. And if you look very carefully on this flower, there's a tick. I didn't see that until I took the picture and blew it up. So it didn't get me, so I guess everything is okay. Hope you're as equally tasty as I am. Stone crop, wild cucumber, and columbine, which I can never see because I'm red-green colorblind, but if I focus, I can. And I'll just go on through past this fawn lily and the phlox. This is an edible variety of thistle. The Native Americans love to eat the roots. And this is from the flower of the copper bush, which is a cousin of the rhododendron. We're near its southern limit. It continues on up north towards the Arctic parts of Canada. And there are more varieties of conifers than you'll find anywhere else, mainly because this area sprouted from the seed bank after the clear cutting rather than being planted with either 1 or 2 species of hemlock or spruce. And as a result, people come in and get charged up breathing those fumes that the plants release. Of interest is the black petal-tailed dragonfly, which was discovered here a few years ago. It's only known in a few localities in North America. and it hasn't changed since it evolved into its present form back in the Jurassic. So it's about 150 million year old family member. And it spends 5 years in the wet mud in the seeps along the road and comes out for 2 weeks, mates, flies, and dies. And it's has a much briefer experience out in the sunlight than other dragonflies, which is an unusual and distinctive thing about it. This is Katie stretching out over one of the seeps that is the source of water for the Filipendula. These things shut down somewhat during the summer, but all it takes is some fog and they'll start dripping again. So a lot of water is taken out of the atmosphere by the cloud cap that hangs on the mountain. And at the top of the mountain, there's an unusual occurrence of glassy fragmental basalt, which forms these big unusual boulders. We'll go through a study about the origin of how these things got this way and what it all means. But this is the distinctive thing about it. This is one of the reasons why the mountains are so steep and tall and so close to the ocean. Their volcanic history is pretty amazing. So I thought I'd start with some modern processes. I usually like to do this because you can either start at the heart of the onion and work your way out, or you can start at the outer skin of the onion and peel it slowly, learning and discarding layers as you go so that you keep things in perspective. The drawback with this is that there's never enough photographs, and and as a result, we're going to run through some of this stuff rather quickly. The most frequently changing thing is the first thing to talk about, and that would be the beach sands and dune sands of the area. This is down there at the south end of Tolovana Park at the south end of Cannon Beach. One year about 2014, any significant winter storms with strong winds or coinciding with high tides. So the summer beach stayed blown up onto the upper reaches of the strand. And then the next year, another beach blew in on top of it and doubled the height. And so in one fell swoop, we ended up with 6 to 8 feet of sand where normally there was about 2 feet. It buried the outcrops, it blew up and relieved a lot of people of concern that their property was eroding. In fact, they started feeling pretty good about having sand dunes in front of their house until along came the next winter and it washed all the sand away. This was looking south towards an unusual rock that crops out at the base of the slope, at the base of the sea cliff below the viewpoint at Silver Point. And I put that arrow in there to note that notch there and this notch here, because there's that first notch on the left. It's during the winter, this rock split open and tipped over, which when you think about it, happens about once a century. And so we had this opportunity to see mass wasting in action. There was already a joint in the rock, and the sand that was underneath the west side of it got undermined. It turns out this occurred during an El Nino when the ocean levels were higher and the waves could reach in farther and do more erosion. Here's another view of it. It's mostly pebble and cobble conglomerate here, a sill of Columbia River basalt, and then more sands and rip-up clasts of, which I'll show you in a minute. It fit together like a catcher's mitt. But the real reason it split open is because my wife obeyed. So much for the jokes. Okay, and at the same time we had the El Nino. There were several storm surges that came in. This drain pipe normally would have been about this far over the man's head, and it was always being buried by dune sand blowing in, and inside of 2 weeks all this sand eroded down to here and shortened the beach, or shortened the dunes by probably 75 or 80 feet. So when you think you've got yourself a stable condition on the beach, think again. It always changes. You never can predict. This is the natural accumulation of dune sand, and the stuff on top of it up here is stuff that we graded and pushed over to improve the view for the people that have beachfront properties. European beach grass is invaded, and it catches the sand as it blows in and makes a huge barrier ridge of dune, which prevents people from seeing the ocean view that they used to have. The city of Cannon Beach has fought through this and gone through all sorts of appeals. And right now it looks like there won't be any more dune grading. So we'll try to keep that in mind. Now, this is a diagram that shows how much sand has changed in its residency for certain parts of the Cannon Beach littoral cell. The Falcon Cove area has lost 16,750 yards of sand in about 20 years. And pretty much, with the exception of Arch Cape here, which gained 12,000 yards, everything has lost sand because it blew up or rode up on the shoreline currents to Haystack Rock and points beyond. Chapman Point gained almost 300,000 cubic yards. That includes the Breakers Point condominiums. The presidential streets gained 31,000, almost 32,000 cubic yards of sand. So the sand that's no longer down here is now up here, and it seems to be staying there. We thought that this would turn around and summer winds would blow it and work it's back down to the south, but so far, especially going back to about 1980, the sand does not seem to be returning. It may be, and it's an indicator of climate change and stronger winds from south to north and from north to south, plus the longshore currents that go along with that. So here's a view of the grading process. And as you might imagine, using a big D10 bulldozer out on the public beach is pretty ugly. And it's very effective, gets the sand out there. And in fact, the whole idea was if we took sand that blew out of the dunes, blew into the dunes and pushed it back into the ocean, it would get spread out in the currents of the ocean and restore the beach farther south. So areas that had lost 10,000 cubic yards might end up receiving 10,000 cubic yards. We haven't had a chance to measure that, but I suspect that's not really going on, given the tendency of the sand to stay going to the north. This is an illustration of aerial photographs from 1939, 1967, and 2009, showing the shorelines and the absence of European beach grass in 1939 versus 1967 and more recently. You can see that a lot of the foredune, which is this white sand here, started becoming colonized by European beach grass by the mid-60s. And by the beginning of the new century, that had all been replanted with European beach grass, and the shoreline had moved something like 300 feet farther towards the ocean. And this is, as near as we can tell, a permanent condition until some unusual event like an earthquake and tsunami comes along. But that remains to be seen. So and if you know me, you know I talk about earthquakes and tsunamis all the time. I'm not going to anymore, at least not as a hazard for us to be concerned about. But this is the mouth of Ecola Creek, and here's a large Sitka spruce stump that most of the stump rotted away, but the roots of the tree embedded in this gravel. Whether this is a recent tree of like a few hundred years old, maybe prior to the previous earthquake, or maybe it's a terrace tree, which could be 80,000 years old, remains to be seen. No one's done a carbon date on it. But it does tell you something, that it's not always what it seems. Fossil wood or old wood like this pops up all the time. For example, down at the north end of Arch Cape, underneath the beach is this old forest and swamp It's mostly slick clay surrounding dead or downed, I should say, downed spruce trees. And this was exposed about 8 or 9 years ago after some unusual storm condition activities. And along one of the kids that was visiting came upon the old cannon from the Shark British gunship that was broken up on the bar of the Columbia River and floated down to Cannon Beach. And they had rescued one of the cannons way back when, which is how Cannon Beach got its name. And here it is. This is the wood base, and this is the cannon. This is the end that delivers the cannonball. And we've got mechanisms back here for improving the aiming tools. So this has been recovered and turned back into a real cannon. I don't know where it is, but it's probably in one of the museums around locally. But this is just a thing for your trivia. At the same time, when all that sand washes away, it exposes the wave cut bench that is underneath the beaches. Normally, this would be covered with about 2 to 3 feet of sand. And these rocks, some of which are cemented together, will skid and slide around when the surf is pushing and pounding. And things act like abrasive sandpaper, and it grinds down the terrace surface here and slowly lowers the elevation of the bedrock under the beach. A lot of this rock gets thrown up at the base of the hill and forms a berm. This is a barrier that the waves break on. Sometimes they wash away and expose the base of the sea cliff to wave erosion, and then we start having problems if houses are up above. Frequently there are landslides coming off of Silver Point, and the area up at the area up at the north end here has a lot of big blocks of basalt tied up in it. Now, if you go down to Hug Point, and I don't know what these pink lines are, but it seems to be we're going to be stuck with them, it looks like. These are outcroppings of sandstone that have this mushroom shape. It's caused by the rocks skidding around in the surf, being knocked against the base of the rock and being harder than the sandstone. The basalt grinds it away preferentially. And so these things, like this one and this one over here, are going to eventually get undercut, and they'll topple and become boulders in the surf. So this kind of stuff is going on all the time. You just don't normally see it. If you go farther north into Hug Point, you can see that the cobbles and pebbles are sloshing around on the beach platform, and that there are some reddish brown masses here that are actually old wood. And you can see the wood sticking out. These are spruce trees. They've been dated at about 3,600 years. They represent forests that moved down off the hill when sea level fell for a brief period in what's called the hypsothermal event about 3,600 years ago. The ocean rose rapidly, then there was some sort of climatic shift that caused the ocean to draw back down a little bit, and these ocean benches became vacant and opened so the trees could grow on them. And eventually, of course, sea level rose again and killed the trees, but their roots are still there. That's a cool thing to find. Here you can see the spruce in growth rings are pretty big. There's also some interesting features of iron oxide cemented beach sand. So now we have the normal typical fine grained sand that the Cannon Beach and the Clatsop beaches are made of. They've been cemented by iron oxide, which forms a crust and a cement where fresh water comes up from springs out of the bedrock. The bedrock has carbon in it. The carbon eats up any extra oxygen that's in that groundwater and reduces the dissolved iron into a soluble form of Fe2+. But when it leaks up through the bedrock and encounters the beach, it meets oxygen in the oxygenated ocean water, and the iron is immediately oxidized to Fe3+, which gives it a hematite red stain, and it binds all the sand together, and we get these unusual towers and ridges and fins. And it's hard to believe they can survive the pounding of rocks. So I guess either they form quickly and rebuild themselves after being destroyed, or they get buried back by the sand, and it's only a few days a year or a few days a decade they actually get to see these things. But who would have thought? So whenever you're out messing around when the tide goes out and there's been some big storms, go down and check and see if you can find these things. It's cinnamon brown in color. It's probably iron hydroxides as well. So the next younger material, the next older unit on the geologic maps that we deal with are the coastal terraces. This is a coastal terrace in California. We have bedrock up in the hills, and then we have this inclined surface that's planar. It's been beveled off by the surf, much like what's going on down here. This sea cliff is comparable to this old sea cliff up here. What's going on is that there's been a high stand of sea level about 8,000 years ago that brought up sea level to approximate elevations that we have now and formed what you see in this photograph. But then the ocean withdrew during the Ice Age when the glacial ice caps locked up all this fresh water. And as a result, it pulled the ocean away and allowed to move out and for the terrace to become occupied. And here in the north end of Arch Cape, you can see this is what remains of a previous terrace. A little further south, these houses are built atop the terrace at Cove Beach. It's about 40 to 50 feet above sea level, almost continuously along Cannon Beach and Arch Cape and down into Oswald West State Park. As this example shows, there's a terrace here, another terrace here, another terrace here, whoops, whoops. And these each represent a high stand of sea level. The land rises slowly tectonically while the ocean is pulled away during the Ice Age. Then the ocean comes back and bevels a new terrace, cutting into the old one, and it creates a stair-step characteristic. And this is where the ice is otherwise held during the Ice Age. This can cause sea level to drop as much as 400 feet. Going on at the same time, there is elevation of the land. This diagram shows the relative height of sea level or of land level with respect to ocean level. And it's changing depending on where you are based on surveys, careful surveys. The land south of Coos Bay has been rising faster than sea level, and the same thing at Astoria. And in the area from Cannon Beach to about Coos Bay, land is rising slower than sea level. So this area up here, the land is emerging from the ocean. This area, land is submerging. And this results in cliffs that are more landslide prone and erosion prone on the central Oregon coast. In the local area, the sea level has gotten up against the base of the hills, and it's actually exhuming old sea cliffs carved into the sandstone. This was a sea cliff 80,000 years ago, and it goes back into these landslides and terrace materials back on the hill here. We can drill water wells and find where the buried sea cliff is located, and it's been slowly being exhumed by rising sea level. Give it a few more decades or centuries, and we'll probably see new sea cliffs emerging from over here. Also included in the in the local areas associated with the terraces are valleys that are filled with subangular, subrounded pieces of basalt and sandstone, like this notch right here. This is a wave cut notch here standing above this woman. This is down at Short Sands Beach. This has since been eroded away and destroyed by waves, but basically it represents what happens when sea level rises so fast that the gravels of the river valley can't be carried out into the deep ocean, and they backfill and stack themselves in the valley, usually burying spruce trees. Sometimes people think these are mud flow deposits that are just left over from the last earthquake, but almost all the wood is over 40,000 years in age based on carbon dating. And on top of these terraces, say like at Indian Beach, there are Indian bins of shell material and fish bones. This is at the parking lot at Indian Beach. So let's move into the bedrock while time allows. This is where I feel more comfortable. Our first place is going to be the Short Sands Beach, Smuggler's Cove area. The bedrock is inclined, dipping off to the south, southeast, southwest, about 20 degrees. This is what's called the Smuggler's Cove Formation. It's about 30 million years old and represents sediments that were accumulating on the continental slope under about 2,000 to 4,000 feet of water. One of the ways we can tell is we have this interesting fossil, trace fossil called zoophycus. Looks like a big, here's a quarter for scale. And our nephew Kyan here is providing other scale. There's more zoophycus here. These things would, there's a worm that lives in the middle, and they put out a feeding tool that goes out and sieves the sediment, and they eat the organic matter in the sediment, and then they move over and do it again. And they just keep marching around in circles as long as they live and mine the organic matter. So zoophycus, and then there's probably shrimp burrows here that he's pointing at. You can see the sediments have been worked by some other organism. Everything here that looks like a little hook or a nook or a piece of wood or a bone or something are all burrows that have been preserved. They're ichnofossils. They're trace burrows. There's even there's a penny for scale. This is, I've concluded, this is just a very small this is happening. I'm saturated. These are spiny sea urchins, little ones. You're gonna have to get used to this. I'm saturated on all the things that I've been thinking about. And there's a few shells that you can find. Most of them are snails that have big fluted rims that allow them to work across the soft sediment of the seafloor, and they get picked up on undersea avalanches and landslides. Speaking of which, here's one in the cliff. This is 40 million year old or 35 million year old undersea avalanche. You can see the blocks here, and then there's in a matrix of silt and clay and a dike, a clastic dike of sandstone from this landslide that came down and squished the water out of an underlying sand layer. A closer look shows the part of the sand that was left behind by the avalanche. Here's the clastic dike of medium to fine grained sandstone. We'll be looking into how these things form. A good example that I've always liked to use is this 1929 earthquake off of the Grand Banks, which triggered undersea landslides. It was a magnitude 7.2 earthquake, and it broke transatlantic cables as the density current flowed down the slope at about 50 miles an hour. And you can tell based on when the phone quit working and how far apart the cables were, how fast the water was moving. And I've always liked this one because the guy who laid the transatlantic cable was Cyrus W. Field, and his grandson, Cyrus W. Field III, was my thesis advisor at Oregon State. So the loops of history start working together here. Arnold Bauma of the Royal Dutch Shell, a geologist, identified turbidites or turbidity currents as the mechanisms for how these sandstone layers form. In this particular experiment, somebody got some dirty water and they released it into a sloped tank, and the density of the dirty water was greater than the density of clean water, so it hugged the bottom and flowed down until it reached the end. These things occur in the ocean and can go as much as 500 miles out across the abyssal plain. Bauma's sequence starts with a landslide up on the steeper, higher slopes of the continental slope, and it breaks up as it moves down slope, and it starts dropping sand as it moves and slows down, and then silt and clay as it goes further out where the velocity of the water is less. And the Bauma sequence is a famous thing that was really one of the hallmarks of sedimentology in the 20th century. One of the things is that it usually is fed by a river, which feeds the continental shelf, and then it has sandbars or shoals underwater that break and liquefy during earthquakes or perhaps under extreme storm conditions. And they flow down slope and they spread out like the Bird's Foot Delta of the Mississippi River, only it's under the ocean, under 10,000 feet of water. And these turbidites, these are known as turbidites. They have their best analog on the surface is snow avalanches. Most of the snow, ice, and rock is underneath, hugging the ground, and a cloud of ice is coming along with it. Turbidites leave characteristic sedimentary layers where in this particular core, very young turbidites have a silty, sandy layer, and then a long, quiet period of clay silt drape that forms just from normal storms and the sediment from storms carefully sifting out of the water. And then another layer forms. In this example from Cape Arago, you can see the entire Bauma sequence. There's this sandstone is forming a trough. It's just like a creek, maybe about 10 feet across or 6 feet across. It's got pebbly sands down here in the bottom, coarse, fairly coarse, that become graded. They form these laminations. They become finer as the velocity of the water slows down. And it gets to a point where it starts forming very fine-grained sand and silt climbing ripples that represent the waning sediment from the cloud as it disperses, as it drains away. And then ultimately there's a clay drape that caps it all. And these things form by the thousands. And you can see them in beach cuts and in rivers and on headlands, wherever these things have been uplifted and exposed by erosion. Now, I'm going to take just a moment to talk about angular unconformities, because the Smuggler's Cove Formation has been warped and folded. It was laid down very much like this diagram shows, with A, B, C, and D being older at the bottom, younger at the top. And then they were compressed from laterally from fault activity and warped to form this anticline. And then it was eroded down to form this surface on dry land. And then it resubmerged and went under the ocean, and new layers were laid down on top of it. The unconformity can represent 100 million years or 1,000,000 years, or even less or more, or something in between. But it represents a long period of time that you can't ignore. And so when we talk about an unconformably overlying sequence of sandstone over limestone, for example, it tells you that the bottom layers were folded and warped, and it represents mountain building. The land rose, the land went back down. And this happens in Clatsop County. This is the type locality for the angular unconformity in Scotland at Sicker Point. Hutton was one of the fathers of geology, and he found this place when he mapped the British Isles. And it's been a place where everybody goes who studies earth science. My wife may not know this, but we're going to go there next time we go to Europe. I want to see this place.
Tom?
Yes.
For some reason, I don't know if this is across the board, but the slides are a little bit delayed. So if you could just advance and take, advance early, maybe we'll catch up
Okay.
when you're
All right.
start on a new slide.
Thank you. Okay, we're at Hug Point in this photograph. We're looking at sandstone cliffs, medium to fine grained sand, sometimes pebbly, fairly thick bedded, massive in places. These represent, these overlie the Angora or the Smuggler's Cove Formation unconformably and are cross-bedded. They have coal beds, for example, in the dark seam up here, there's some coal. There are cross beds that represent sandbars of water moving in one direction, transporting sand over a previous layer and dumping it into deeper ponds downstream or downriver or down ocean. Oops. And you can find them sometimes forming little troughs. Sometimes they're planar, but represent relatively high velocity water. The sandstones are clean. Any silt and clay that was coming down along with them was transported out, carried away farther downstream, and deposited ultimately out in the ocean. You can see this pocket knife for scale. I've lost it. If anybody finds a jade pocket knife that looks like this, let me know. It's mine. The sandstone is fairly massive. It's not evenly cemented, so it tends to get a dimply pattern on it. It's pounded by these basalt rocks that are thrown by the surf, which cut caves. It's a great place to go explore caves. Take your kids and families there. Go again and again because it changes every time. The sandstone also rips up pre-existing layers of fine sediment by floods and currents. And so, as you can see in this, there are these angular fragments of a dark carbonaceous siltstone or mudstone that was torn up by high velocity currents and laid down along with the pebbles and cobbles. Probably thinking about easy rafting through white water, or a little slower perhaps. I'm not sure exactly what the velocities would be. Here's a view of the Angora Peak sandstone with unequal cementation, giving it this lumpy texture. First, when I looked at this, I thought, man, look at all the cobbles and pebbles. But if you follow these seams, they go right through some of the lumps, if you will. And this is not uncommon. It could have been a potential reservoir rock for the petroleum industry, but it's been opened up by exposure from erosion, and anything that could have gone in there ended up venting into the atmosphere. So there's no petroleum or natural gas potential in this sandstone. The sand is made up of a lot of lithic fragments, which means rock fragments. They include volcanic rocks like this white piece of pumiceous rhyolite. There's quartzite pebbles, which is metamorphic quartz sandstone. There's coal. There's various kinds of igneous and metamorphic rocks. These, with this penny for scale, these rocks represent white quartzite and gray quartzite. There is no quartzite in Oregon to speak of. And there's very little in Washington until you get over near Spokane and points farther east. And in Idaho, northern Montana, there's the what's called the Belt Supergroup. It's 2 billion-year-old sandstones that have been eroded and transported down the river and deposited in the Angora Peak sandstone as fragments. So it tells us a lot about this sandstone appears to be from the Columbia River. And it also picked up in this next to this dime where there are even pieces of coal. So it was eroding coal beds as it came through, though they are no longer around and we don't know of any that are of economic significance. They nevertheless are there and are eroding. Now, this particular photograph with the pocket knife for scale is a dark piece of driftwood that has been drilled by teredos, which are wood-boring marine clams. It's a marine fossil. And you can see inside of each one of these tubes, there are fine grain, medium grain sands that have sifted in. And apparently the wood got so waterlogged it sank and got buried in these pebbly sands. So this is telling us that this sand was deposited in marine conditions. And the coal that we talked about earlier is a freshwater deposit. So we have both marine and freshwater. And here is a photograph of the teredos themselves drilling out wood. I'll back it up, compare the diameter. It's about an inch to an inch and a half diameter for the biggest hole here in this teredo wood. And it's about the same for this piece of driftwood. So we have an interesting feature there. And another thing we have in this particular photo with the golden brown sandstone, there are reversible cross beds. In this direction, you see they're going almost horizontally, and just above them, they're inclined down at about 45 degrees. Then they're going horizontally, and then inclined down about 45 degrees. This is called herringbone cross bedding, and it represents sands deposited by a sandbar continuously as the tides went in and as the tides went out. And so this is telling us that we're dealing with an estuary. And we know it's the Columbia River because the sediments, the pebbles and cobbles have come from the upper reaches of the Columbia drainage, not from any local source. So the moral of the story is we're in the estuary of the Columbia River down at Hug Point. And the place to go look for its analog is over here in Astoria. There's a sandbar out there. The tide goes in and the tide goes out. It's flat across the top. It's got cross bedding in it. It's that's where Hug Point was 15 or 20 million years ago in the Miocene. Also going on not too far away is what's called the conglomerate of Cape Falcon. And here these people are standing on well-cemented large boulders of various kinds of volcanic rock that have no other correlation or we have no idea where they came from. No one's figured it out yet. But it represents a high energy deposit of probably a steep submarine head that filled with underground, under the ocean submarine flows of large rocks. There's another view of it. Some of them are big rocks, most are smaller. And they represent only this little area, just at the very south end of Cove Beach and Cape Falcon. I'll wait for your photos to come through. In this particular geologic map, now these yellow lines represent the boundaries of the Rainforest Reserve acquisition. Cove Beach is over here on the far left, and the Cape Falcon conglomerate is just along the shoreline down here on the very west edge. So we're going to go What we're also looking at, this unit that's labeled TAA, is the Angora Peak Sandstone. And it forms a big horseshoe loop going around and represents the estuary of the Columbia River. Overlying it, where it says TAC, is mudstone, which forms in deeper, quieter water. So the land is warping down. The Angora Peak Sandstone rests over the stride unit, which is the Smuggler's Cove unit. And it was formerly above land being eroded, hence the angular unconformity. And then the sandstone was deposited on top of it, and then mudstone was deposited on top of it. And then ultimately, this pink unit, which is volcanic glass and rubble, was deposited on top of it. We're going to take a look at some of this. Here's our old friend, the turbidite. This is down at Silver Point, south of Cannon Beach. Here's a large channel of sandstone that tapers out and disappears over here on this side. Every one of these ridges, these light bands, represents a sandstone that the Balma sequence. And here they're a little thicker up here. So these are the same kind of steep ocean conditions, you know, a few thousand feet deep, with undersea avalanches being triggered probably by earthquakes. When the sand comes through, it leaves these light bands. The dark bands represent carbon-rich layers of silt and mud. They scour each other out of the way, especially where the sandstone is coming through, and leaves these various surges represented here. One surge is down here in the middle, and two or three in between, and a larger surge, probably from independent landslides that came a little bit later. You can see they get scoured away by later surges of sediment. And up here you get what are called load casts, which I'll show you in a photo. Here we go. The dark mud. Wait a moment for you to all get caught up. Dark mud is soft and pliable, and when these turbidites come through, they dump a tremendous amount of heavy sand on the soft gooey mud, and it squishes it down, but it doesn't squish down evenly. It forms these protuberances, these ball and pillow structures that are a few inches to maybe a couple of feet across, and represent the surge of new sediment, followed by even younger sediments that are higher up. So the turbidites are there. The turbidites are rich in quartzitic pebbles and cobbles, and this is at Silver Point as well. There's a large chunk of laminated sandstone on the right-hand side that has not been broken down by the currents when this thing was ripped up. The description of rip-ups is best illustrated by this photograph, which shows fine-grained sands and silts that have been torn up by the currents tearing across the seafloor and tumbled along for a while and then dumped in a pile. They didn't get ground away, they just got rounded because they were a little sticky. They held together. There was enough cohesion for these things not to break apart. So we have rip-ups, and it's all part of the Balma sequence. Up in the north part of Ecola Park, there's some folded sandstones and mudstones shown here in this photograph between Ecola Point and Indian Beach. It's just another indicator of some of the deformation that's gone on since these things were laid down. I just had to throw this one in. This is my father-in-law providing scale. This is a sandstone clastic dike. Remember the little one we had down at Short Sands Beach? This is up near this new water tank for the community of Lewis and Clark near Miles Crossing. And that's about a 2-foot wide dike of medium grain sandstone that was fluidized by an earthquake, and it ejected up into a muddy silty capping layer and injected. And then groundwater has oxidized the edges of it to make it stand out a little bit. That's pretty cool. It's clastic dike. Once again, telling us that this area had steep enough slopes to support turbidites. So the question is, where did the estuary go? And how long did it last? Obviously, it had to leave in order to be overlain by dark laminated muds of deeper water. So where did the Columbia River go? Well, as it turns out, this blue unit on the geologic map between Nicolay Mountain and Wickiup Mountain, up near Napa Junction and Swenson and the Wana Mill, is the eastern edge of the estuary complex. And it's overlain by lava flows, which are painted orange and red and represent lava deltas that were that moved into the ocean. We're going to explore these in a moment. So here's my cartoon that I thought I'd be creative with, and I don't know why I threw this in. It didn't work the last time I tried running it. The modern Columbia River Canyon is over here on the far left side. Cape Disappointment and Clatsop Spit are at the mouth of the Columbia River. Astoria, Swenson, Napa are along the edges of the river, and the lava delta, lava flows came down and hit the ocean right about where Napa is located. And they flowed, as you're going to find out, down a submarine canyon that went southwesterly instead of east-west. The east-west canyon that we have now is only a few million years old. This old canyon was 20 million years old. Okay, so and that is where we're going to start talking about the lavas. So right now it's 7 o'clock. I'm going to have to start running along in a hurry in order to get this done. So I'll try to be brief. We're going to talk about flood basalts. The diagram that's on the screen has in brown the Columbia River flood basalts. These are lava flows that were big enough to cover as much as 65,000 square miles in a single eruption. There were 300 eruptions. Not all of them were so big. And they were able to flow, be erupted probably within weeks, rarely in less than a year to 2 years maybe. And they flowed from 100 miles into Idaho all the way out to the Pacific Ocean, hitting the ocean near Napa, indicated by the vertical yellow, dark black line. And the rainforest reserve is down at the very far end. So these lavas were erupted from the Chief Joseph Dike Swarm, where an entire length of one of these eruptions might be 100 to 200 miles. And it has poured this lava out, and it flooded like a giant lake, developing a skin on the surface that kept the heat in so it could still stay fluid. There were no lava cones, there were no cinder cones. There are very few constructive volcanic features other than just simply the flat lake of lava. This shows the boundaries of the Columbia River basalts. That also includes the Steens Mountains. The reason I threw this diagram in is that the origin of heat that made the Columbia River basalts was not the subduction zone. Like the Cascades, it was from a hot spot, which is presently under Yellowstone National Park. It's being fed by some anomalously warm area down there in the mantle. And if you go back in the direction of motion, you can find additional calderas like the one that's in Yellowstone now, sequentially going all the way over to the south end of the Steens Mountains, where the McDermott caldera is about 16 to 15 million years old, the same age as the majority of the Columbia River basalts. So this hotspot has burned its way over to Yellowstone. It erupted, basalts were erupted, mostly probably because the boundary between accreted terrains such as island arcs, such as Japan, underlie Oregon and Washington to the Idaho border. And within a few dozen miles of the Idaho border, you suddenly cross over a suture zone where you're now dealing with continental rocks instead of island arc rocks. They have different chemistry, they have different isotopes. They tend to form different kinds of lavas. These are rhyolitic lavas, say 65 to 75% silica, prone to making obsidian and pyroclastic flows. The Columbia River basalts, maybe 48 to 50% silica, and they are so runny you could almost pour them out of a cup. So there are different kinds of lavas, different chemistry. Has a little to do with the origin of the materials that evolved them. So this is the stratigraphy of the basalt field. There's a 310 lava flows. The ones that are painted orange and red and dashed red are those that made it to the ocean. About 13 lava flows made it into Clatsop County. The screen shows these maps. I'm waiting a moment for it to come up. The oldest unit is known as the, oops, oh no. Hang on. Oh, I hit a button.
If you want, I can also.
I got it.
Okay.
Thank you. I would like to blow it up if I could. Oh, there we go. Presentation mode. There we are. Sorry about that, folks. The lava started erupting first down in the Steens Mountains, then they moved up into the Hells Canyon area, then they continued farther north up into the Blue Mountains, and then even further, ultimately wrapping up north of near Wenatchee. So there was basically the expansion of the hot underground plume of magma coming up that apparently lost its heat after a while. Now, the lavas that made it into the Clatsop County area are some of the Grand Ronde basalts. These are aphanitic lavas. They don't have any crystals in them. Unlike the Wanapum basalt, there's one called the Ginkgo flow, or the Frenchman Springs lavas, which made it down to the coast. It's got a few crystals, and I think I've got a picture of a rock. There it is. Here we go. These are feldspar crystals. There's about 3 to 5% feldspar in this Ginkgo flow. This is what makes up Haystack Rock. This one over here is one of the Grand Ronde lavas. It doesn't have any crystals of any size. They're very fine grained. And these make up most of the mountains in Clatsop County, most of the volcanic mountains in Clatsop County. The Columbia River basalts in the Grand Ronde region over near Northeast Washington, Northeast Oregon, are stacked one on top of the other. You see they're one after the other. Closer you are to the origin of the lavas, the more you're going to see these things. They develop distinctive columnar joining. This is known as entablature at the top and colonnade at the bottom. Oh man, I did it again. Got to stop doing that. And they're basically cooling joints. The lava shrinks, it solidifies and hardens, and thermal contraction causes them to pull apart, usually in hexagonal columns. They can be real tall post piles like this, or much shorter, but they're very distinctive. So we'll just flip through, march through these as quick as we can. This is a, wait a moment. Once in a while, you can find the dikes that fed the lava up to the surface, exposed by erosion. And this is one of them in this particular unit. In this photo, the lava flows have columnar joining that's vertical, not perfect, but it's perpendicular to the bedding plane. And then the columnar joining of the dikes of basalt are like cordwood. And you can see it on both sides of this gap. This is cooling joints where things are cooling along the surface of the injected dike. And that's about all you'll see as the source of lavas for a Columbia River basalt. The lavas continued down the Columbia River to about the Wanna Mill and Napa, the city of Napa. This is the rock quarry run by Teben Brothers. And you can see they're mining lava flows, these columnar joints. They've been making a mint out of this thing for the longest time. Unlimited amounts. Nikolai Mountain is made of all this stuff. It tells us that they were deposited on dry land. And I just couldn't resist. I had to show you, sometimes the lavas develop a crust around them and they flow under the surface of the lava flow after it's hardened, but they continue to flow, pumping lava down through distributary channels. Sometimes these things drain out and make lava tubes, empty caves, like up on some Mount St. Helens or over at Bend or down in the Northern California area. This is in particular one is from Iran. And I just thought this was the best example of columnar joining in a feeder that I've ever seen. So I'm sharing it with you for that reason. Okay, now what happens when the lava hits water? The water chills the lava, turns it to glass, causes steam explosions that shatters the rock. It breaks it apart into fine-grained rubble. Some big chunks, sometimes there'll be bodies of lava that are pushed out through cracks and gaps and form the equivalent of large blobs of toothpaste, maybe up to 5 or 10 feet across or smaller. And they are usually deposited in the water until the water is filled up, and then the lava flow continues out over that and leaves behind columnar joints of lava flow instead of lava rubble. That's what this shows. Another view of pillow basalts is shown with this friend of mine who's 6'3", give you an idea how big those pillows are. The glass has been destroyed and knocked loose by the surf because this is a Cape Disappointment. It's a different kind of lava. This is seafloor lava, but it's pillows, and you can find pillows wherever you look, wherever there's basalts and there's water. One of the reasons we call them pillows is indicated by this one above is Dan's hands. You notice it drapes over the pillow underneath it, and it drapes over the pillow underneath it, which drapes over the pillow underneath it. So it's like a stack of soft feather pillows that you throw on top of each other and they deform around each other. Sometimes the pillows just slowly crackle and fall apart. In this particular photo of taken down at Indian Beach, you can see these large pillows or blocks of lava that are auto-brecciating. They're just crackling and falling apart on their own, but they didn't make it. They got bound up and preserved, and then the surf exposed them so we could look at them. These are 15 million years old. They've been sitting underground for the longest time, and only recently have slid down on a landslide to the beach where the surf has cleaned them up. And this is at Indian Beach. The glassy fragmental rubble of a pillow complex the pillows can break apart if they roll too far. And they will create stony interior pieces of rock and glassy exterior pieces of rock, which are shown in this particular photo with my foot for scale. The blue-black rock represents the glassy rinds, more or less obsidian, of composition, of basaltic composition, and finer matrix supported, we call it pillow, boy, I'm going to start thinking here. Basaltic hyaloclastite, glassy fragmental rubble, and it binds itself together and creates massive deposits in Clatsop County. Sometimes you can find the pahoe-hoe texture of lavas that were erupted onto the surface and cooled and then got carried into the water. Particular photo showing the typical ropes. But for the most part, the glassy fragmental rubbles still are glassy if they haven't been hydrated by groundwater too much. This particular little piece I'm holding, you can see there's white patches of calcium carbonate, zeolite, and quartz and agate, which are minerals that are carried and deposited by hot water in solution. And so these lavas not only were chilled by the ocean, they also heated up the pore water trapped inside, and chemical reactions took place. This helps to bind them. It also helps to rot them. Sometimes they turn into just brown earth. But this is what makes up the tall mountain peaks around from Nikolai Mountain down to Angora Peak. So I'll just go through a few of these quickly. More rubbly deposits with glassy rubble in them and orange-brown oxidation products. And you can see places the rock is really heavily cemented with hydrothermal quartz, calcite, and zeolite. This is Gene, a volunteer for the Land Conservancy, providing scale. And they form very prominent hoodoos and spires up on the mountain peaks. You see them on Sugarloaf, for example. There are peaks that spires that must be 100 feet tall up there. There you can tell that they're made of rubble and that they have large pieces. There's a big pillow in this particular hoodoo that's probably 8 feet across, maybe 10 feet across, up on Angora Peak. And sometimes they have a few rounded rocks in them. So that we know that there was rounding in a surf zone somewhere up current, somewhere by the Napa Swenson area, maybe. And these, you can see that they're not angular, they're rounded to subrounded. So it tells us there was a little bit of fluvial action or wave action, maybe on the surf along the ocean. Given half a chance, these things will decompose and rot down to form these big spheroidal boulders. So we call this spheroidally weathering basaltic hyaloclastite, and it's common in the forests around Arch Cape. They are fun to try to get rid of. You have to chisel them apart, or because they're too big, usually for a bulldozer or an excavator to pick up. But they're very distinctive, and they're always a pleasure to come across when you're out hiking around. And one of the reasons they're round is the same reason ice cubes start off as cubes coming out of the tray and go into the drink, and then they melt away, which is no different than weathering in place. A cube of rock will turn into a sphere of rock given enough time. And that's what we just saw in that previous photograph. This is important because on the mountain, the jointing in the rocks supports the percolation of groundwater that rots the basalt and turns it into brown earth, which is then washed away by water and ground. And then the rock begins eventually to decompose and fall apart until nothing remains. But in the process of doing this, these rocks lie on the slope and they move down slope, and they roll sometimes, or they just imperceptibly creep along. And sometimes they lap over each other in such a way that the soil can wash away and it leaves a cave behind. So quite naturally, this is where the black bears like to come and den up for the winter, because they need to dig out an even bigger cavity under these rocks, or they can just make do with what they've got. But you can find tree damaged or bear damaged trees on the rainforest reserve because of the number of bears, and this is a wonderful thing to have. So wherever you go on the rainforest reserve, you see these particular boulders, giant boulders all over the place. You don't see that on Saddle Mountain. Here's Saddle Mountain with the trail going through the main part of the saddle, up past the snow and up to the summit. There's only 2 boulders on the entire face of the mountain. Why does Saddle Mountain not have as many boulders as Angora Peak and Onion Peak, or the hills near Onion Peak? And I think it has to do with the fact that there are big faults down near the Rainforest Reserve, in contrast to up near Saddle Mountain. And the cracks that are created by the regional stress field as these faults move are like that aluminum ice tray, cracking the rocks. And so that lets the water drain in and rot the rocks and turn them into boulders. This doesn't do that. It's not cracked, not like that anyway. At least that's my guess. Anyone, if you're out there listening, Carolyn, you're free to weigh in on that. I know that everybody wants to say something about it. There are, as you can see, the mass wasting processes on these steep slopes. There are debris flows where the soil lets go, takes all the topsoil and plants with it, and it goes down the hill. Few trees will grow in pockets where the soil is stable, but in some places, the forest gets too big. And as a result, the whole forest slides off and it opens a bare spot, which then turns into a grass ball. But give it enough time, it'll get a new forest on it again. We can find the remains of debris flow forests down at the base of the mountain on all sides of the Saddle Mountain. All right, and we're getting pretty close to my deadline, so I'm gonna wrap it up here. This is a quick cartoon, a simplified geologic map that Al and his wife Wendy put together that shows Clatsop County. We have a lava delta over near Napa and Wana, and it's pushing into the ocean over the Tuarine sandstone in the Astoria Formation. And from there, glassy fragmental lava deposits in Elk Mountain, Wickiup Mountain, Saddle Mountain, Humbug Mountain, Kidder's Butte, Sugarloaf, Onion Peak, Angora Peak, and Neocani Mountain mark the submarine canyon of the Columbia River. It was draining down to the estuary at one time down here at Hug Point. It moved up here during that period of time, and the density currents coming out of the Columbia sort of entrenched this thing, and it continued to flow dirty water, and it continued to cut down through the sediment layers that were accumulating on the seafloor in this, between these two dashed blue lines. Outside of the dashed blue lines, sedimentation continued and it built up. So it grew higher on the sides, on the flanks, and it got deeper in the axis of the submarine canyon. And it's left a range of mountains that are about 5 miles wide and about 2,000 to 3,000 feet high. In contrast, in comparison to the modern Columbia River Canyon off of Astoria, it's about 5 miles wide and about 2,000 to 3,000 feet deep. So it's in the inverted topography where once there was a canyon, now there are ridges, remnant piles of lava left behind to form a discontinuous ridge. Astoria Canyon, to show you what it looks like, what it really looks like now. Astoria and Cape Disappointment are just over here on the far right. The canyon starts at about the 600 foot below sea level line on the edge of the continental shelf. The lavas, or the dirty water of the Columbia River, drains down this canyon and meanders around things, past and through these pressure ridges that are produced by the subduction zone in the earthquakes. These things will move and rise during the next earthquake and produce the tsunami that comes in and smacks Clatsop County. But this is the modern analog for what we had in the previous slide, showing pretty much the same thing, only filled with lava. So a more believable example of the inverted topography of a canyon filled with young lavas. This is Table Rock near Medford. And you can see it's flat on top. It represents an andesite flow that came out of the Cascades following the river and filled the valley and self-leveled itself. And then down cutting by the river on both sides has washed away the softer materials that the canyon was originally cut in, leaving behind this residuous table of basalt or andesite. So this can happen. This is called inverted topography. It's a good principle. The cartoon shows the lavas coming out of the Columbia River, building out a lava delta and pouring down into the soft sediments. to move out laterally between layers until they find it easier to lift the seafloor and fill giant sills, which are locally called in Europe saucer sills. They're relatively flat and they bend up at the edges. Al likes to call them silly dikes, and it doesn't work for me at all. I don't know why he ever invented that term, but I'm condemning him here publicly for the first time. But these things that leak up to the surface and form the many wash rocks and reefs that you see off of Cannon Beach and Arch Cape right now, like Castle Rock, for example. So I'm gonna go past this and go past this. Let's see what some of the implications are of the lavas on the local geology along the shoreline. So here we are at the south end of Hug Point, big sill of basalt intruding into the sandstones. The cave is being preferentially formed because the waves can pluck the jointed volcanic rock out of the sandstone. This is what it's like when it's been protected from being shattered by cold ocean water by surrounding sediments. So there are sills and irregular piles of lava that erode out of the sea. It's just an example photo, just to show you that you can't look at round rocks or angular rocks or breccia piles or sills. You've got to look at them all. And this is just an example of what an intrusive lava looks like. They also tended to boil water and push the delta complex at Hug Point out of the way. The soft sediments were being invaded by these hot fluid basaltic lavas, and as a result, things started squirting all over the place. When you see these disjointed features poking out of the cliff when everything else was otherwise normally layered, it tells you that there's been a lot of energy invested into the system. These, as things move around, you can see behind this guy's rock hammer, there's a little bit of basalt sticking out, and that crack between the basalt and the sandstone is enough for hydraulic pressures of waves to get in and break out the sandstone and the basalt and make sea caves. And you can see pebbles in part and in folded sediments that are almost vertical, whereas they were originally laid down almost flat. They've been pushed out of the way by the invasion of these basaltic lavas and mixed up against other things. Also, hot water features are present in these things. We're going to start talking about pepperite complexes. When the ocean, when the lavas come up and erupt onto the seafloor, they boil water, and they can explode, and they can intrude, and you can get a whole spectrum of textures and flavors of textures that tell you that what once was nice and smooth and easy to appreciate is now starting to get pretty gnarly. In this particular photo, we have veinlets that have been cemented probably by quartz in the sandstone that makes up this little sea stack, and then the weathering has knocked out the uncemented parts, so you can see how the hot water penetrated through the sand. Also, there were periods of steam explosions which blew apart the sandstone and the dark laminated carbonaceous siltstones that overlaid them and blew the whole thing apart along with the basalt itself. And in this particular photo with the pocket knife for scale, you can see the blue-black carbonate or carbon-rich siltstone that was shot probably 200 feet above the bottom of the ocean by these massive steam explosions. If these were up at sea level when they exploded, they probably would have been thrown a minimum of half a mile. So these things are going off like giant bombs. And then they fall back in the crater that was created by the explosion, and they never got moved again. That's why when you see sharp angular rock fragments like this, oh, there was something quick and powerful, and it didn't continue. And it's it's a great prospecting tool. If it happens in a geyser system, that's where the gold's going to be, if you're looking for gold. But this is a pretty spectacular outcrop. This is the money outcrop for a lot of people in the business. Some large pieces of sedimentary rock got peeled back, and you can see they have planar surfaces on their top and bottom, and almost perpendicular joints across the ends, but they're surrounded by many other smaller fragments. It's at about 400 yards north of the Hug Point, the northern of Hug Point, the proper promontory. In other words, at the south end of Arcadia Beach, but north of Hug Point. You can see this in the sea cliffs. And of course, the sandstone's been warped and folded. You go down to the right 200 yards, the sandstones are dipping the other direction. So they were making space for the invasion of the lavas. And they can see where the lavas pressed and pushed their way out laterally away from the sill. They form sea stacks where the soft surrounding mudstones wash away and leave behind the hard igneous rock. And that's why Cannon Beach has so much beauty in its scenery and so many bird habitat sea stacks for seabirds along the Pacific coast. This is the place because this is where you get a lot of sea stacks because of the geology. And I am just 7:30 now, so I have a few photos that show sea cliffs out around Cape Falcon, and I think that's about it. If you want me to go for it, Lynette, I'll be glad to.
Well, let's see if anyone has questions so far. If not, then we can just continue. I posed in the chat. If you have questions, you can enter them there, but I haven't seen any. So if you want to take a few extra minutes and people want to stay on, then please stay on.
Okay. All right. Well, I'll be quick. I'm sorry I'm taking so long, but you know, when you've got thousands of slides, you just can't resist but put them into the talk. This is south of Cape Falcon in a cove, and you can see the cliffs are jointed intrusive basalt, and it's breaking off and being ground up by the surf, making large boulders and a lot of smaller pieces. This blue-black color is the typical color of Columbia River basalt. That's aphanitic. This is the Grand Ronde flow. Doesn't have any crystals in it, it's absolutely astounding when you get back there. If you go in at low tide, plan to get out before the tide changes, and look around. Great opportunities for photographs. Here it is again. In fact, you can get black sands, kind of like you don't have to go to Kilauea or the big island of Hawaii in order to find a black sand beach. You've got them right here at the south end of Clatsop County. Just take a gunny sack and you can haul out 10 pounds or 20 pounds, just like everybody in the world wants to do. The basalt intrudes into the sandstone of the Angora Peak sandstone of the Astoria Formation. And here you can see the edge of the basalt penetrating into the sandstone and protruding in about 4 feet before turning back. It's very cold, it's chilled, glacier, blacker, darker rock than over here, which, well, dark, it's not quite as dark. And this is a sign that it's glacier, and this is less glassy. It had less chilling from surrounding sands and watery, rich sediments. Show you a few pictures. It's such an enchanting place. It's really worth going to look. That's Keith Chandler from the Seaside Aquarium. He was on a specimen collecting trip. This was before the Cape Falcon Marine Reserve was created. He can't do that anymore, so he doesn't go back here like he used to. He knows his way around it, though. There are resting traces for harbor seals. You can see them here on this basaltic feldspathic sand. They look like what you would expect from a big wheelbarrow or a large tire rolling down the beach to the water. These critters come up and rest up here, and then they work their way back down to go fishing. Sea caves, as you can see, are forming. There are a lot of sea caves. But you'll also notice there aren't a lot of barnacles, and there aren't a lot of sea stars. They can't survive here because the pounding is too great. So they get polished off as fast as they can grow. That's pretty impressive wave energy there. Probably waves 30 to 40 feet high pounding away and moving boulders, I'm sure. There's the black pebbly sand, coarse grained sand, if you will. She teaches art at the community college. And sometimes the caves form where cracks coincide and they meet in the middle and make a, and this is the beginning of one. That's why it's so cool to go explore. You can see, looks like horseneck barnacles are about the only thing that can really survive there. Okay, there's a view of the landscape. I guess I'm going to talk a little about Saddle or Haystack Rock just for a brief moment. Haystack is one of these secondary submarine volcanoes that was produced by the eruption, re-eruption of the ginkgo flow of the Frenchman Springs lava, the one that has the crystals in it that I showed you in the rock. This is one of the later lavas that came in after most of the Columbia River Canyon had been filled with lava flows. As a result, the lavas didn't go down the submarine canyon like the Grand Ronde flows. They ended up moving across the seafloor and coming out to the ocean at about where Seaside is. And then that makes up the hills above Seaside. You can find this kind of lava underground about 700 feet under the surface over at Circle Creek at near the golf course in Seaside. And it apparently goes underneath the sill that makes up Tillamook Head and re-erupts as Haystack Rock. So the Frenchman Springs lavas are envisioned to have made a rubble pile of a lot of pillows and a few dikes, feeder dikes of lava coming up from the ground. And you can see in the middle of the diagram where it says Haystack, that's all that remains of this big complex. It's being fed by something underneath, sills and dikes that are connected through a common plumbing system. And as it turns out, you can find feldspar containing cobbles up and down the shore from Arch Cape to Ecola Park. They didn't all come directly from Haystack Rock. They also came from other places where the lavas pushed their way through sediments, ran in a pre-existing sill of basalt and glued itself to the underside and spread out underneath and went around it. You can find these. They're easy to see in the sea cliffs, particularly. So this is what makes up Haystack Rock. In the Tillamook Island, this is I think this might be my sum total story. No, there's a couple more. The Columbia River lava delta is up near the Wanna Mill and Napa. It forms various peaks going down to the southwest, out to the ocean. It actually continues a little into the offshore too. There are USGS surveys that found continuation of Neocani Mountain and the Cape Falcon sill, another 5 to 8 miles. And it served as a barrier to stream propagation. Most of the rivers that drain to the north for the water supplies for Cannon Beach, Seaside, Warrenton, and Astoria get their water from streams draining off the lava piles. And the same thing happened when the river of the Nehalem tried to go through this. It bounced off and had to sneak its way down and come out just at the south end of Angora Peak, or excuse me, Neocani Mountain. So it's been a major feature in the evolution of the landforms of the coast, north end of the Coast Range. They're basically off to the flanks of the Tillamook Highlands oceanic volcano, which was about 55 million years ago when it formed. I won't bore you with the stories of other rivers that owe their origins to similar processes, but there is a significant control of streams that once drained from the Cascades to the ocean without going up to the Columbia. But once the Coast Range rose and lifted out of the ocean, that's interrupted the flow of those rivers and forced them into the Willamette Valley, made the Willamette Valley and the Willamette River, and it made it up to the landforms we know now. The source of the Yellowstone hotspot, it seems to have been underneath Tillamook County about 50 million years ago. And as North America continued to shift westward, it overrode it. It seems to have been the source of heat that provided the Crooked River caldera and Smith Rock State Park. These are big rhyolite flows, very much like Yellowstone. It's largely covered by basalt flows, so you don't see it, but in this particular area, it does show well. And these are the cliffs of the pyroclastic deposits. They're very much like you see in Yellowstone. And we'll be quick about that and call it an end with the critters of the land and sea saying goodbye. Thank you. Are there any questions?
Folks would like to know if you're going to do a field trip.
Yes, I haven't scheduled it yet, but if anybody wants to get in on it, I'm sure we can figure out how to make connection. Let's say communicate through the Land Conservancy.
Well, Tom, thank you so much for compressing thousands, if not millions of years into an hour-and-a-half presentation. That's very impressive. And I think that your geology professors would be very impressed as well. So thank you. I give you an A+.
Oh, thank you.
Folks, thanks for joining us this evening. If you're interested in learning more about North Coast Land Conservancy or any of our upcoming events and news, you can join our e-news and mailing list by visiting our website, nclctrust.org. And we don't have a presentation up on our website yet, but we will be offering one in June. So check your email. That will be going out. That information will be going out at the beginning of June. So stay tuned. We appreciate your support, and we have a lot of kudos. And thank you to you, Tom, from our participants here. And I will type the website to the chat here because folks are asking. There we are. Thanks for sharing your passion, Tom, Kathy says.
Oh, my pleasure. So I think the important thing is bear in mind that even though we look at those mountains every day and we're used to looking at them, it's like not seeing the forest for the trees. This is the only mountain range of its kind on the West Coast. And it's one of the more steeper and more extreme. We call it these mountains the Galapagos Islands of Clatsop County, because they did rise out of the ocean. They were surrounded by water for a while. They went through some process somewhere between 10 and 2 million years ago of rising up out of the ocean and shedding all the soft sediment that was around them, so that we end up with these real steep, real high mountains, and that isolated organisms. And that's why we have special species and communities of species that you don't find anywhere else. You just go down to the Tillamook Highlands, which are almost as high, but they are missing a lot of these organisms. So it's a very unusual habitat and well worth conserving and studying. I think as we go by, time goes by, we're going to find all sorts of unusual things that you don't find anywhere else. And it was always the intent of the Parks Director for the state of Oregon to secure those before they got harvested for timber, but we'll grow it back. It's going to take a couple hundred years, but there's no doubt about it. We've got the time to pull it off. And it's a reservoir of genetic information that may be called upon someday in the future if climate warming continues and gets out of control. They may only survive there. And that's one of the cool things about this project.
We will look at these mountains differently. So folks are asking, this is being recorded and we will post it online. And once we get that online, we'll share that link via our monthly e-news. So with that being said, everyone enjoy the last hour of sun while it's out, and go have dinner if you haven't done that already. And thank you so much for joining us. Thank you, Tom.
Thank you.
Good night.
Have a good one.